everyone, and welcome back. Today we're going to be continuing our exploration of Markov processes and look at a few applications that I find quite interesting, and they can also be branched out into several different fields as well. So the first application I want to look at is sometimes referred to as a discrete time queuing process. So let's take a look at what this process is. So we're going to be working on the state space 0, 1, 2, 3, and so on. So all of the non-negative integers. And we're going to be taking into account at time t is equal to 0, we have that many people waiting in line for something, whether it be a taxi service, a shopping line, ordering food at a fast food restaurant, and so on. So at time t is equal to 1, two things are going to happen simultaneously. First, a customer is going to be served, provided that there is any customers to serve. That is, it's going to decrease by 1, so emphasis on a customer, not multiple customers. And also, a certain amount of customers are going to also arrive in that line, and that number is going to be represented by x1. Right, so x0, x1 are going to represent how many people arrive into this line for some service at time t is equal to 0, t is equal to 1, and so on for t is equal to m. Right, so there's a couple of variables you could be keeping track of. One, how many variables arrive at time t is equal to m, and also the total number of customers that are waiting in line at t is equal to n, which is the variable that we're actually going to be trying to model via a Markov process, right? So let's define, so let's assume that yn is the total number of people. So the total number of people in line. So the total number of people in line. And let's see if we can actually sit down and model this. So if we have, x0 waiting in line at t is equal to 0, what will be y1? So y1 will be equal to x1, the number of people that arrive in line at time t is equal to 1, plus how many people were waiting in line before minus 1, because one person was served, right? So that's going to be x0 minus 1. But this only makes sense if x0 is greater than 0, and y1 would just be equal to x1 plus 0 if x0 is equal to 0. So that's what y1 would be equal to. So let's take a look at what y2 would be. So y2 would be equal to the number of people that arrive at time t is equal to 2, plus the number of people that were in line at time t is equal to 1, minus 1, because one person is going to be served. But this, of course, only makes sense if x1 is greater than 0, and y2 would just be equal to x2, provided that x1 was equal to 0 as well. So from this little pattern, you probably can easily generalize this at time t is equal to m. So generally speaking, yn will be equal to xn plus xn minus 1, provided that xn minus 1 is greater than 0, and yn will just be equal to xn in this scenario that xn minus 1 was equal to 0. Okay, so let's just take a look at what we have here. So yn depends only on the values that were in this space before, right? So what we have here is xk is or at least we're going to assume, a sequence of independent random variables. And let's assume that yk, at least by construction, is a Markovian sequence. It's a Markovian sequence of random variables, right? So we're going to be assuming that the number of people that arrive into this queuing process are independent of each other. Now that's not always in practice true, because if you see a long line, you probably are not going to decide to wait, right? So, sometimes that depends, especially if the value of yn is extremely large. So that's one modification you could impose. So now that we have our sequence of random variables that we're going to be marking up via a Markov process, i.e. yk, we have to deal with this fact that, this is a piecewise function. So if you plan to implement this into a simulation in whatever language you prefer, dealing with a piecewise function, which would just be a sequence of if statements, probably is not the best way to do this. So what you can do is that you can actually bring this into one line if you prefer. That is, you can write this as yn is equal to xn plus the maximum value of 0 and xn minus 1. Right? So let's just see if this even makes sense. So if xn is equal to 0, then how many people, well, technically if xm minus 1 is equal to 0, then what exactly are we going to have here? So that means there's no people to sort of subtract from 1. Therefore, however values, sort of come into this picture, xn, we're actually going to have just those amount of people that arrive. So if xn is greater than 0, then we have that yn will just be equal to the number of people that arrive, which is just going to be equal to the maximum of 0 and xn minus 1, which should be equal to xn minus 1 minus 1. So xn minus 1 minus 1. So you had two little minus 1s there. Because xn minus 1 would be negative, because xn minus 1 would be 0. And if we consider the case where xm minus 1 is greater than 0, that means xm minus 1 minus 1 would be greater than or equal to 0, and in case if it's equal to 5, that will be the value that we have. So yn will just be equal to the number of people that arrive plus the number of people that were there before minus 1, and that gives us the exact model that we had. Okay, so now that we have this Markovian process, now our goal is to find our stochastic matrix P for our Markovian chain PYT. Okay, so what exactly will this be? So we need to see if we can build some probabilities for this process. So what we're going to do is we're going to define the probability that the number of people that arrive is equal to k is equal to pk, and pk obviously is going to be a probability from 0 to 1. K is going to belong to the interval 0, 1, 2. That's how many people arrive at time t is equal t. And let's assume, since this is an unbounded interval, we need the sum from k is equal to 0 to infinity of pk to be equal to 1. So a nice candidate to model the probability for xt probably would be, I don't know, maybe a Poisson or something related to that on unbounded above interval, bounded below by 0 discrete. Right? So now that we have some structure for this, and I'm not going to explicitly define this because I want you to have a little bit of freedom of this. Let's see if we can construct our stochastic matrix P. So what are we going to have? So let's assume, again, yt is going to map 0, 1, 2 to the interval 0, 1, 2, and so on. So this is the number of people that are waiting in line. That's going to be our state space S. So what's the probability that we transition from state 0 to state 0? Right? State 0 to state 0. So we have no people in line, and we then go to, again, no people in line. So the only way that that can happen is if no people arrive. So that's going to be having a probability of P0. Now, what about the probability of transitioning from S1 to S0? So if we have one person, and then on the next iteration we have 0 people, that means we only had one person in line, they were served, and therefore no people must have arrived, else we would have more than 0 people, right? So in this case, again, no one arrives, and that again would give us P0. Okay, now what about S2 to S0? So at time t is equal to n, we have 2 people. On the next iteration, we have 0 people. But how can that be? Because we only can serve one person on each iteration. We can only go from S2 to S1 or S3 to S2, provided that no people, of course, come. So this is going to give us a probability of 0. And same thing with S3 converging to S0. That's also going to be 0 as well. So you get an infinite sequence of zeros because only one person can be served at a time. right? But if you modify this queuing process to serve more than one person, or the number of people that you're serving as a random variable, this can, of course, change, right? So if we look at our stochastic matrix P, what we have here up to this point, so 0, 0 is going to be equal to 0, 1, 0 is going to be equal to P0, and then we're going to have zeros everywhere else. So that's sort of what we have here for our stochastic matrix P so far. All right, so let's see if we can figure out the rest of this particular matrix. So that's from 0 to 1, 1 to, or 1 to 0, 2 to 0, 3 to 0, 4 to 0, and so on. So what about the rest of this particular process? So let's look at S1 to S0. So S1 to S0. Or actually, let's go from S0 to S1. S0 to S1. So the only way to go from S0 to S1, that means we have 0 people, which means nobody can be served on the next iteration, and then 1 person came, right? So the only way that that can happen is if the probability of people coming would be equal to P1, because 1 person came. Now if we have, for example, S1 to S1, that means we had 1 person, which means this person is going to be served, therefore it's going to decrease to 0. And then in order to go to 1, that means 1 person must have came. So the probability that 1 person came would again be P1. And similarly speaking, if we have S2 to S1, how can we get this? So since we had more than 1 person here, 1 person would be served, so that would go down to 1. And then it stays at 1, which means no people came. That means the only way that that can happen is probability 0, or not 0 probability, but probability distribution value 0. Right? And if we continue in this fashion, what would happen to S3 to S1? So S3 to S1. So that means since we had 3 people, 1 person is going to be served. That's going to go down to 2. We can only stay at 2 or increase. We cannot go to 1. Therefore, that's going to be probability 0. And S4, S5, S6 down to S1 will also be equal to 0. So once we take a look at our stochastic matrix P, we're going to have what? So we have P0, P0, 0, 0, 0 on row 1, and that's going to continue indefinitely that way. And then we're going to have P1, P1, P0, 0, 0, and so on. So you might want to pause this video and think about what the rest of this matrix would look like. So on the next row, you're actually going to have P2, P2, P1, P0, 0. And the next you're going to have P3, P3, and then decrease 1 by 1, P2, P1, P0, and so on. The next row would be P4, P4, P3, P2, P1, P0, and zeros everywhere else. So that would be what your stochastic matrix would look like for a discrete time queuing process, provided that you can only serve 1 person at a time. Let's look at our second application. Suppose that you have a node or a point or a location that can branch off into k is equal to 0, 1, 2, and so on, branches to new nodes. So for example, let's assume that we start off with just one little node, and let's assume that it decides to branch off into 2 nodes, one here and one here, right? And those nodes can then branch off into their own number of nodes. For example, we can go 1, 2, 3, so 1, 1, 1, 2, and 1, 3. And then this other node can branch off into, 2, 1, and 2, 2. And this process goes on. So let's assume that 1, 1 attempts to branch off, but it can't. 1, 2 cannot branch off. 1, 3 decides not to branch off. 2, 1 decides to branch off into one node. Let's call it 2, 1, 1. 2, 2 decides to try and branch off, but it cannot for whatever reason. And then finally at t is equal to 0, t is equal to 1, t is equal to 2, and t is equal to 3. 2, 1 attempts to branch off, but it can't. That's usually what we refer to as extinction of whatever we're trying to model in this particular thing, because if you do not have any nodes, then you have nothing to branch off from. So this type of process is sometimes referred to by the picture and also the name, a branching process. right? So let's assume, similar to our previous example, let's assume that the probability that the number of branches it branches off to, which I'm going to assume is xt. So for example, this is xt is equal to 2, xt is equal to 3, xt is equal to 2, xt is equal to 0, 0, 0, 1, and 0. So let's assume that the probability of xt is equal to k is equal to, let's say, again, pk, pk belonging to 0, 1. With the same assumption as before, the sum from k is equal to 0 to infinity of pk is equal to 1. And again, a Poisson distribution probably would be a reasonable amount, because on average, how many branches does each of these branches branch off into? Okay? And we're going to impose, so let yn be the total number of nodes at time t is equal to n with y0 initialized to be equal to 1. Of course, you can modify this, but usually that's not really that interesting, but you easily can, right? So at t is equal to n, so here we have 1, here we have 2, here we have 5, here we have 1, and here we have 0. And that's usually extinction. Okay, so once we have this, then what type of process are we going to have? So let's see if we can build our stochastic matrix P. So what is the probability of transitioning from state 0 to state 0? Think about that. So if you have no nodes to branch off from, then you're guaranteed to branch off into 0 nodes as well, right? So the probability of that is going to be equal to 1 because we have nothing to branch off from. Nothing to branch off from. And what is the probability of transitioning from S0 to SK, where K is not equal to 0? Take a moment and think about what you think this is. This is going to be equal to 0 for the same exact reason. Right? So if we think about our stochastic matrix, what does this automatically give us? So 0 to 0, that's going to be 1. 0 to 1, that's going to be 0. 0 to 2, that's going to be 0. All the way down to 0, right? So now we just need to figure out what the rest of this matrix is going to look like. So let's take a look at S1. So the probability of transitioning from S1 to S0 is going to be equal to what? So we only have one node, and it's transitioning to absolutely nothing, right? It just dies, right? So that means the number of branches it produces is 0. So that's obviously going to be equal to P0, right? And obviously, if I change this to the probability of S1 branch off into S1, that's going to be equal to P1, and I can generalize that the probability of transitioning from S1 into SK, that's going to be equal to PK. So now we can evolve our stochastic matrix and add our next column. So we're going to have 1, 0, 0, 0, and so on, and here we're going to have P0, P1, P2, P3, and so on, right? And now we need to start building the rest of this matrix, and this is where things get really, really interesting. Right, so now we're going to look at the probability of transitioning from S2 to S something. So let's go from S2 to S0, right? So we're starting off with 2 nodes, and we're going to 0 total nodes at the next time step, right? So that means this must die off, and this must die off as well. That means this is going to be equal to the probability 0 times the probability of 0. So this is for the first node, this is for the second node. So that's going to be obviously P0 squared. So that's the first entry in our sequence. Now let's look at the probability of transitioning from S2 to S1. So again, we start off with 2 nodes. Let's call this node here and this here. And we're going to have 1 node at the next time step. So for example, you could have this event, or you could have, what other event? You could have this node die off and this node branch off into our one little node. Right? So this is going to be equal to what? So this is going to be equal to the probability of 0 times the probability of 1 plus the probability of 1 times the probability of 0. And I'm actually going to keep it in that form, although you can abbreviate this as 2P0, P1 if you so wish. Now let's take a look at PS2 to PS2. You might want to pause this video and see if you can figure this out on your own, because if you can, the rest is actually going to be very straightforward. So again, we're going to have 2 nodes, and we're going to go to S2. So for example, the first can branch off, and this can die. Or the first can branch off into 1, and the second can branch off into 1. Or the first can die off, and the second can branch off into 2. In either case, we have 2 nodes across all of our sub-branches. Okay, so we have 3 events here, so what would be its probability? So if we look at this from left to right, we're going to have P2 times P0 plus P1 times P1 plus P0 times P2. Right? Do you see the pattern yet? So what would be the probability of transitioning from S2 to S3? So that's going to be equal to P3 P0 plus P2 P1 plus P1 P2 plus P0 P3. And that would be that. I hope you see the pattern now. So let's see if we can nicely generalize this little sequence. So what's the probability of transitioning from S2 to Sk? This is going to be equal to the sum across all ij such that I plus j is equal to k. Because notice that from 2 to 3, we have 3 plus 0, 2 plus 1, 1 plus 2, and 0 plus 3. Those are our index, and the index sum must always be equal to 3. And what are we exactly summing up? We're summing up the product of pi times pj. We're summing up that particular product. Right? So that's from 2 to 3. Note that we have 2 index associated to this. I'm obviously not going to put this in our stochastic matrix because that would be quite ugly, but nonetheless that is the pattern. So what about the probability of transitioning from P3 to Sm, for example? Again, m can range from 0 to infinity, discrete-wise. So take a moment and think about what you think this is going to be equal to, generally speaking. So this is going to be the sum of across all I, j, k indices, such that I plus j plus k is equal to m of the product pi, pj, pk. Right? Because we're going to have 3 nodes that are all going to branch off into their own respective branches. And this would be that particular probability. So you practically range across all values of m, where m ranges from, again, 0, 1, 2, to infinity, down that column, and that's going to give you the 4th row of that particular stochastic matrix, right? And you can generalize this onwards, but the pattern practically remains the same. Now, the next type of application that I want to investigate sometimes is referred to as a multi-state dependency process. And what exactly is a multi-state dependency process? So suppose, as an example, that every day can either be cloudy or sunny, and that the weather today depends on the weather the past 2 days. The past 2 days. Emphasis on the word 2. So that means, for example, the probability that the weather today is equal to some particular state S is equal to, or this distribution is dependent on completely the weather, for example, at time t is equal to n minus 1, and also n minus 2, right? So that is, this, at least on the surface, is not Markovian. And you're like, well, I thought we were talking about applications of Markov processes, right? So this strategy, this multi-state dependency process, can actually be viewed as a Markov process if you sort of blend these into one variable, right? So how we're going to do this so that this can be viewed as a Markov process, else we're going to have like a 3-dimensional tensor or a 3-dimensional matrix or something like that to deal with, which can be a little bit messy. So our strategy is to pair consecutive days or states together. So pair consecutive states or days into pairs. Pairs of 2. Right? Pairs of 2. For example, if you have a multi-state with order 3, then you would pair it in pairs of 3. Okay? So what exactly would our state space S be equal to? So we have 2 individual states, cloudy or sunny, for each of the days. So for example, 2 consecutive days could either be cloudy, 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 sunny, and then sunny, cloudy, or sunny, sunny, right? So that would be our state space for pairs. right? And obviously the cardinality over state space is going to be equal to 4, and that's going to determine the size of our stochastic matrix P. Okay, so let's assume that our time domain space is again discrete, so 0, 1, 2, 3, and so on. And what we're going to do is we're going to define our variable xn to be equal to Sn to be the weather on day n. But in terms of this pairing, this n, this Sn, corresponds to the weather on day n and day m minus 1, right? So when you look at these pairs, that's today, that's today, that's the day, that's today, or the day of reference, and the one before it is the day before that day of reference, okay? So let's actually, before we get into the building of our stochastic matrix, let's just look at an example just to make sure you understand this notation. So let's assume that x7 is equal to the state SC, right? So how are we going to interpret this? That means it is cloudy on day 7, and it is sunny on day 6, right? So again, this corresponds to the day of reference, and this corresponds to the day before. That would be x6. So if we look at, for example, variable x6, what would this be if this is in the same exact world? So keep in mind, S is on day 6. That means this must be S as well. And then the next variable to the left of it is, of course, up for grabs. For example, that can be C. So what does this represent? So again, C corresponds to day 6, and this corresponds to day 5, right? So here we only need, so therefore we only need the distribution of x6 to model the distribution of x7, right? So now we have our Markovian process, so now we can easily build our stochastic matrix for that Markovian process, okay? All right, so let's take a closer look at what we have here. So a couple notes here before we start building. So again, if we transition from SS into SS again, for example, these must be, or these correspond to the same day, always, right? So that means that when I write this particular notation, this is three consecutive days of sunshine, right? So that's just 3 consecutive days of sunshine. And another note that you probably have already figured out, as I've already mentioned, if you have ij, because technically we can have more than sunny and cloudy. So if we have from ij and we transition to kl, for example, there must be some things that are true. For example, let's assume that this is xn, let's assume that this is xm plus 1. One thing that must be true is that j and k must match. Else, the probability of transitioning from ij to kl will be equal to 0, okay? Because we can't change history, right? So once we have that, now we can build our stochastic matrix, or a stochastic matrix. So let P be equal to the following, right? So let's do CC, CS, SC, and SS. And do the same exact order here, CC, CS, SC, and SS. Let's just draw some lines so our matrix doesn't look too ugly. So the first thing that I want to do is figure out all the cells in this particular matrix that has to be equal to 0, which should be half of them. So keep in mind, we're going from CC into these states here, CC to CS, SC, and SS. So for example, if this is day 5 will be the first entry over here for which I have aligned. So they have to match. So we have C to C, C to C, C to S. Well, that's not possible at all. So that's going to be 0 and 0. And the rest of that, is up for debate on what you think it should be. And then similarly, we have S here, and we cannot go into C, so that's going to be 0 and 0. Same thing can be said about the last column. That's going to be 0 and 0. And we cannot go from C into S, that has to be 0 and 0 as well. Now, the other numbers are up for grabs of what you think those distributions should be equal to. For example, we can do 0.7, 0.3. If you think it's more likely to go from 3 consecutive days of cloudy to 2 consecutive days of cloudy into sunshine, for example. And here we can do 0.2 and 0.8. So that means we have, it's more likely to go from cloudy into 2 days of sunshine rather than from cloudy, sunshine, cloudy. So that's pretty much what is going on here. And here we can do, for example, 0.9, 0.1, and 0.4, and 0.6 to complete that particular structure, right? So that would be an example of this stochastic matrix for this meteorological application. So now notice that we do have some zeros here, and we actually have quite a few of these states here that are 0. So the first question that you might be asking is, well, is this a regular matrix? So if we calculate the Perkins number m to be equal to our dimension, keep in mind this is a 4 by 4, so this is going to be 4 minus 1 squared plus 1, that's going to be 3 squared is 9, plus 1 is 10. The only thing that we have to check is to see if p to the power of 10 is regular, and that's going to allow us to see, does there exist a unique limiting distribution or not. But actually, you can check, for example, p squared, and you should be able to see that this is actually trivially regular. It is trivially regular. So if it is trivially regular, that means there is a unique limiting distribution of our process, which is going to be equal to, let's call it P of xt, where xt is our pairs of weather consecutive days. So since we have a regular stochastic process or a regular Markovian process, the primary eigenvalue that you need to analyze for the long-term distribution obviously would be eigenvalue 1. So it's a stochastic matrix, so eigenvalue 1 is always going to be the case, and you can find that an associated eigenvalue would actually be any scalar multiple of 3, 1, 1, and 2. So if this is the case, if we add up all of these entries in order to turn this into a probability vector, we're going to have 3 plus 1 is 4, plus 1 is 5, plus 2 is 7. So our associated equilibrium vector, which some people call it, or the limiting distribution, is going to be equal to Q is equal to 3/7, 1/7, 1/7, and 2/7. So that is going to be our limiting distribution for this particular process. So if we write these as decimals, just to get some approximations going for communication purposes, that's approximated as 0.43, 0.14, 0.14, and 0.29. Approximately, right? So what do we exactly interpret this as? So keep in mind this first row corresponds to CC, then CS, then SC, and then SS, and the day of reference obviously is going to be the last day. So how can we interpret this limiting distribution? So that means in the long term of weather, so let's focus on sunshine. So sunshine is going to be row 2 and row 4 of this. So we're going to have about 0.14 plus 0.29, and that's going to be equal to what? So that's going to be 0.43, which is 43% of days will be sunny, approximately, and similarly about 57% of days will be cloudy, right? So cloudy, let's assume that's a cloud. It's not a very happy cloud, but it's still a cloud, right? So those are 3 different variations of applications that you can definitely use Markovian processes for, in particular discrete time queuing processes, branching processes, and also when you have multi-dependency Markov processes as well, where you want to sort of, have dependency on multiple objects, but you sort of want to force it into Markovian structure so you can analyze with the typical theory. Hope you enjoyed this video, and I'll see you in the next one. Take care.